Okay, so ladies and gentlemen, we're going to be doing the section on chemical equilibrium today. So I'm going to get started straight away. Okay, so we are looking here at the section called chemical equilibrium. I really enjoy the chemical equilibrium section. It's question 6 in your exam paper if you're writing the NSC CAPS paper. And I know this because for the last 2 years it's been the question that I've been marking. And I am under the belief, or most people are, that if you start marking chemical equilibrium, you never leave it. Okay, we don't actually choose it, but you never get out of it. So this is a section that's very close and dear to my heart. And it's also a section that's viewed to be, not that way, that's viewed to be relatively challenging. So it is one of the hardest sections in almost all papers. It's viewed to be the hardest section. So please just make sure that as I go through this, you understand what we're talking about. Okay. The first thing that I want to start with is other names, because quite often they don't use the word chemical equilibrium. They say something along the lines of dynamic equilibrium. Okay, so dynamic equilibrium or just equilibrium. And I need you to note that all of those things mean exactly the same thing. So please don't get caught out in an exam because they're suddenly talking about dynamic equilibrium that you say, oh, we never did this. Or if they ask for a definition of equilibrium, dynamic equilibrium, chemical equilibrium, they're all the same definition. So please don't get caught out with wordiness. So the definition of chemical equilibrium is it's a situation where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, this means, in a simple sense, that your starting materials turn into products at the same rate as your products turn back into starting materials. So we have a situation where the two reactions are happening at the same rate. Now, in order for us to ever be able to establish a chemical equilibrium, we need two things to be present. First of all, we need a reversible reaction. If the reaction itself is not reversible, you can't have the products turning back into starting materials. So examples of irreversible reactions, if I boil an egg, I cannot unboil that egg. If I set a piece of paper on fire, I cannot unset that piece of paper on fire. So only certain reactions go in both directions. If you've been doing the section on fertilizers or you've already managed to get that far, if not, when you eventually get there, you'll see that some of their reactions establish equilibrium and others don't. One of the main reasons for that is whether or not the reaction itself is reversible. The second thing that we need is we need a closed container. So if we have a closed container, what it means is that our products cannot leave the vessel that the reaction's happening in. If you've got a reaction happening in my coffee cup, and it produces a vapor or gas, and the gas leaves, that gas can't then react and turn back into something back in my coffee cup because it's left the system. So we must have a reversible reaction in a closed container. The simplest example that I can probably give all of you, and it's the example I always go to, is that if I have a bottle filled with water, so example, juice bottle, any bottle, Coke bottle, you half fill it with water, and then you put it outside in the sun, we can establish an equilibrium here, where we have water in the gas form and water in the liquid form. Sorry, can you please put that back in the freezer? I've just been served ice cream. I don't know what's up with my son. Okay, and you're going to have a situation where the water that's in a liquid form turns into a gas form because of evaporation, and as that happens, what will happen is that the water level here will drop down, okay, because we're having less and less liquid water and more of it's turning into water vapor. Then what's going to happen here is that the water vapor is going to condense and turn back into a liquid. And what will happen is eventually this water level that I was talking about that went down will just remain in one place. I'm moving the wrong thing. Yeah. Okay, if, however, it later gets a little bit colder, then we may end up with a situation where we're no longer in equilibrium and the water level rises. But while we're in the situation where the water is evaporating, pushing different buttons, sorry, the water is evaporating at the same rate as it's condensing, we can say that we're in equilibrium. And when we're in equilibrium, what's really important is that the concentration, or concentrations if they're multiple things, of the starting materials or your reagents and the products remain constant. So they're not always equal to each other, but they remain constant. They remain the same. Okay. That means that if we're drawing graphs, and we're going to eventually get into the idea of how we draw graphs. I apologize, I'm not drawing straight line graphs here. These should be straight lines. If I'm drawing graphs, we get two types of graphs that we're going to get. The one graph looks specifically at rate, and the other graph looks at concentration. And they're going to look a little bit different when they show that we've reached equilibrium. If we're looking at a rate of reaction, you've already done rates of reaction, reaction rates is the fastest or the highest when we have the highest concentration of starting material. So a forward reaction usually starts at the highest possible point and then moves downwards. So this over here could be for our forward reaction. Oh my goodness, my pen is misbehaving today. Reaction, okay? And then my reverse reaction, because we usually start off with no product. Like if you fill this with water, you wouldn't have water vapor there yet. It's got to be made still. My reverse reaction starts from 0 and increases. Where the forward and the reverse reaction are the same rate. Oh my goodness. There we go. Then we know that we're in chemical equilibrium. So in this particular case, I can say from here onwards, that is chemical equilibrium, because the forward reaction rate and the reverse reaction rate are the same. And that's because both of them, the rate is on my y-axis, and that's what I'm looking at. Whereas when we deal with the concentration, which probably should discuss here, and I'm going to interrupt myself, but it's important. My y-axis is rate. My x-axis here is either called time, or sometimes we can just call it reaction coordinate, like how long the reaction has progressed, but usually time is what we go with. So we usually have concentration or rate versus time. Yes, reaction coordinate usually is not for this particular section, it's for another one. So maybe scratch that from your thoughts. Here, my concentration, my reactants start at the highest value and then go down. Okay, so these over here are my reactants or my starting materials. And then if I were to do my products start from nothing and then we gradually make them. Okay, so reactants decrease in concentration, products increase. And although my lines are not perfect here, if I were to draw a dotted line here and pretend that those were both perfectly horizontal, as soon as my reactants or products remain constant, I can then assume that I'm in a situation where we're in equilibrium. So when you're in equilibrium, the rate of your forward reaction equals the rate of your reverse reaction, because your starting materials are turning into products at exactly the same rate as your products are turning back into starting materials. Key important word that they often like bringing up here is the idea of dynamic. Dynamic means constantly changing. So it means that your starting materials are turning into products and your products are turning back into starting materials, even though it doesn't look like it. If you look at this picture over here with the water and the water that's a liquid and the water that's a gas, you can't actually see there that some is evaporating and some is condensing, and it's not the same one just going around, okay? Because it's different molecules that are changing. I always use the example, I'm terrible about coffee cups. There are coffee cups all the way around my house all the time because I'm drinking tea, and teacups everywhere. And I could talk about the fact that the rate at which we wash teacups is the same as the rate at which I dirty teacups. But the teacups that I'm using at any one time are not the same teacups. There's a complete cycle of them getting washed and then reused. So the idea here is that it's still changing, it's dynamic, it's moving. All right. Can I quickly check before I go any further? Does everybody understand the idea of what a dynamic equilibrium is or a chemical equilibrium. I think most of you hopefully got that. The only thing that I have to caution very carefully against, sorry, is in the x-axis, yes, Christine, it's time. Okay, and usually time, gosh, time could be measured in a whole bunch of different things. All right, so it's usually time in seconds, but it depends on what our units are that we're going with. So the last thing that I just quickly wanted to emphasize here, I've just forgotten what it was, no I didn't, is that we've got to say the rate of the forward reaction is equal to the rate of the reverse. In a multiple choice, they're often going to try and catch you up by saying the forward reaction is equal to the reverse reaction. And it's very tempting because it looks the same, but it's missing the idea of, completely of the word rate. Okay, Alex Martin, yes, they're the same thing, although chemical means that it's referring to chemicals happening, and dynamic, so you can get an equilibrium in physics. So when we talk about chemical equilibrium, we're specifically referring to the fact that it's chemicals that are reacting and forward and reverse reactions that are happening. The chemical equilibrium and a dynamic equilibrium are the same thing. It's just that we sometimes use the word dynamic to show that it's changing, chemical to show that it's involving chemicals, and equilibrium if we know that both of those must be applicable anyway. All right. So dynamic, just quickly going, is changing. So, oh gosh, one last example of dynamic. Dynamic just means that it's not that if you look at this picture, you might get the idea that your reactants stay the same and your products stay the same, so nothing's happening. That's not the case. The reactants are constantly turning into products and the products constantly back into reactants. So you need to understand that there's still a reaction that's happening. There's still a change that's happening, and that's why it's dynamic. Okay, another example that gets me into a little bit of trouble with my family at home is I always use the example that it's like tidying up the house. If I'm tidying up the house as fast as my kids are messing it, we're in a dynamic equilibrium. All of the mess is always new mess, but it's not that I'm not constantly tidying, and it's not that they're not constantly messing. It's just that where they're messing and where I'm tidying are not the same thing at the same time. Okay, so it's just the idea that it's changing. They're just all the same words that we can use to describe the same thing. Okay, I'm now going to move on, and we're going to discuss Le Chatelier's principle. I'm just quickly moving all of my bits that I know you can't see around. There we go. Okay, so this is Le Chatelier's principle. And Le Chatelier's principle was examined 2 years ago, and it caused such issues in terms of the definition. I'm going to strongly recommend that you go with whatever definition your teacher's given you, because I must be honest, in marking this definition, I can tell you where the marks are, but I can no longer tell you what the wording is. So the ideas behind Le Chatelier's principle come as follows. When a disturbance is applied to a system in equilibrium, it will cause the system to act so as to counteract the disturbance in order to re-establish, re-establish a new equilibrium. So when we marked this, and it was for 2 marks, we marked it according to the idea that you have to identify that originally the system was in equilibrium, that there was a disturbance that acted on it, and that afterwards we would form a new equilibrium. If I could look at a question and say, this student is aware of the fact that there was an equilibrium, then there was a disturbance, then we went back to a new equilibrium, they get all the marks. Now, just so you know, I know that some of the students that are watching this are not doing the CAP syllabus and they're doing the IEB syllabus. The IEB syllabus does not have this last line about re-establishing a new equilibrium. Okay, I'm sure that if you do put it in, no one's going to panic about it being there, but just that you are aware that is one of the small differences between the CAPS definitions of chemical equilibrium and the IEB definitions. So everything that I'm teaching here is specific to CAPS, but I'm aware of the fact that IEB left this establish a new equilibrium out, because when I learned this definition, it never had re-established a new equilibrium. Okay, the next thing that's important, so that's your first mark, is that we need to know that the system will act so as to counteract the disturbance. Now, this is where I recommend you look very carefully at the definition that your teacher's given you, because counteract is not the same as, I think oppose was accepted, but I've got to be very careful. So oppose was okay, reduce wasn't. And there were a whole bunch of words that meant very similar things, but didn't get you the mark. Please be very careful. Counteract will get you the mark. All right, so just be very careful that you understand the wording here and how it fits in. So I always use a very simple example, and I don't have a cloth anywhere, so I'm sending out a hint that I want a cloth. But imagine I had a cloth hanging down here, and I applied a force to the cloth that causes a disturbance. The cloth will move, and then as soon as the system, the cloth that's been displaced, yay, thank you, my cloth has arrived. So if I've got a cloth here, now this is a physical example of kind of an idea I'm illustrating. So if I apply a force, okay, I've applied a disturbance. The system wants to remove the disturbance, which means that right now the cloth is pushing down on my hands. And if I then allow it to, it will reestablish its original equilibrium or original position. And what's happening here is kind of the same thing. You disturb it, it wants to return to what it had originally. So I find that when I approach Le Chatelier's principal questions, I have a set approach that I follow. Please note, not every one of these steps is going to get you marks, but it will give you a firm understanding that will eventually get you all of the marks. You will get all of the marks, but you're not getting a mark for everything that you do. Some of it, there aren't marks allocated. So the first thing that I always try to do when we've got a disturbance to an equilibrium is I try to identify the disturbance. I'm going to quickly discuss with you what the three disturbances that we can have are. So first step is identify the disturbance. Second thing is identify how to remove the disturbance. Third thing, identify which system is favored or which reaction is favored. And the last thing is to answer the question. Now, the reason I specify that you must answer the question is that sometimes the question isn't, are we favoring the forward or reverse reaction? The question might be about a color change. Quite often with chemical equilibrium, they like to ask questions that involve N2O4 being in equilibrium with NO2. And hopefully by the end of today, you'll all have it cemented in your mind that NO2 is brown. It's a brown gas. Nitrogen dioxide, if you didn't know, is brown. I'm going to do this, you guys won't see it. I'm underlining it in white, okay? And I'll not write it in white, it's not going to work. But this is a clear, colorless gas, which means that in this particular case, if the forward reaction is favored, we will end up with a container going darker in color. We're making more brown gas, and our colorless gas is turning into our brown gas. The mixture in the container gets darker. If we instead favor the reverse reaction, then it gets lighter. So you may not get away with just being able to say forward or reverse is favored. Your question may be, is it going darker, lighter, or staying the same? Your question may be about the concentration of nitrogen dioxide. So forward reaction, this is just important that we get these ideas out there. If the forward reaction is happening, we are turning, this is called dinitrogen tetroxide. Actually makes sense. Di 2 nitrogens, tetra 4 oxygens, and this is nitrogen dioxide. Okay, so if we favor the forward reaction, we can say that the concentration of N2O4 will go down because we're using it up. If we favor the forward reaction, the concentration of nitrogen dioxide will go up because we're making it. So the answer to the question at the end is just a reminder from me that you mustn't go forward or reverse reactions favored and leave it there. You're going to miss the point of what you're trying to put together. All right. I hope that this makes good sense, because we're now going to go into the 3 factors that affect equilibrium, okay, and then look individually at each of them. I'm hoping that in today's lesson we'll manage to get through all of the Chatelier's principle as well as the basics of calculating Kc. I know it's quite a lot, but I think we should manage to do it if everybody's managing to keep up. Okay, so the next thing is, which are the factors or the disturbance, the factors that can change and affect equilibrium? Okay, question, how do we know that the nitrogen dioxide starts with a low concentration? We don't necessarily, but it probably will because it's a product. So our assumption when I was talking about that it goes up and that it goes down is whatever it starts on, it goes up from there, or whatever the other one, it goes backwards. Okay, just quickly, I see I've missed a couple of questions in here and I'm going to try to go back through them. Please go over the dotted line on concentration. Oh gosh, Tasneem, I don't even know where that dotted line was on concentration. You're going to have to come back and check. Okay, I'm going to try and get to all of your questions. You may need to ask them just now. So, gosh, all right. So I've got quite a couple of questions about, okay, Cameron, can you hear me? Cameron?
Yes.
Okay,
yes.
Cool. This is going to work a lot faster. What was the bit that you weren't certain about? Can you explain? I can even probably get this bit back. Okay, so Cameron, what bit do I need to re-explain here? I presume it's here.
Sorry, I'm not understanding which one's favored and which one's not favored.
Okay, where? I haven't yet favored or not favored anything. I randomly just said we're favoring the forward reaction. That was just random so that people could follow the change or the answering of a question may depend on whether the forward or the reverse was favored. We haven't yet got into why the forward or the reverse would be favored. Okay, I've still got to get to that. Does that kind of answer your question? Maybe. All right, Tasneem, quickly.
Sorry, no, I'm so confused.
Yeah, but
sorry.
Which bit, Cameron? You're allowed to ask.
The forward and backwards.
Okay, so when I'm talking about here.
Yeah.
Okay, so in any chemical reaction, we show that it's a reversible reaction by having an arrow forwards that shows the forward reaction and an arrow backwards that shows the reverse reaction. Are you happy with that? Yes?
Yeah, thank you.
This reaction, was that the bit that you were confused about?
Yeah.
Oh wow, okay. So the
right,
way
okay.
that we
I'm
show
sorry.
that something is, don't worry, this is why I'm here and why you're allowed to ask questions, is that sometimes I assume that everybody knows certain things. And when you don't, that's why it's so important for all of you to speak up. Because I can promise you not everybody has the guts to speak up. But if you don't understand it, there's probably someone else as well. Okay, so thank you for that. So when we show the reaction is reversible, we show a double-sided arrow. As teachers, we sometimes get lazy and we make it look like that. Yes, Tasneem. Okay, Tasneem, I can't hear you. All right, let's just quickly go. Alex, do we always assume that the forward reaction decreases in concentration? No, it depends what you're looking at the concentration of. Next question, what are the square brackets for? It's okay, you guys, I'm here to answer questions. Square brackets mean concentration. Okay, so square brackets around the name of the substance.
So,
yes? Yes, Tasneem? You're allowed to speak.
So,
Yeah?
so for the forward reaction,
Yeah?
if the concentration, concentration will decrease for the forward reaction, and if the forward reaction is favored.
No. If the forward reaction is favored, dinitrogen tetroxide will turn into nitrogen dioxide. If I were to imagine here in my red pen that we're talking about the forward reaction happening. If we use the word is favored, it doesn't mean that the reverse reaction doesn't happen. It just means that more forward reaction happens than reverse reaction. So more starting material will turn into product than product will turn back into starting material. As soon as we're talking about favored, we're not saying that one doesn't happen and the other one does. We're saying that both happen, but one happens more. Okay? The word favored is vitally important in this section. So if we start with dinitrogen tetroxide and we're turning it into nitrogen dioxide, and the forward reaction is favored, it's going to mean that the N2O4 turns into NO2 faster than the NO2 breaks down into N2O4. Because this is turning into this faster than this is turning into this, I've made a big arrow and a little arrow. That means that overall we're going to have a net production of nitrogen dioxide. We'll be making more nitrogen dioxide than we're breaking down. So therefore, the concentration of nitrogen dioxide will go up, and I show this with an up arrow. The reverse reaction, because we're using up the N2O4 so fast, it's going to have its concentration decrease. So what you've got to realize here is we've got two reactions where N2O4 goes into NO2, but NO2 also goes back. And in fact, if I'm 100% correct here, I must put a 2 in front because this splits in half, becomes 2 nitrogen dioxides, and if we do the reverse reaction, they join together. So on this side, it's 2 monomers joined together, dimer, and here we've got 2 monomers on their own. Okay, so it's a bit of a complicated reaction. Okay, so the square brackets around anything is a shorthand for concentration. You do need to know this because we're going to use it in your KC calculations that I get to a little bit later. Square brackets means we're dealing specifically with concentration. So if I wrote square brackets, and this has nothing to do with what I'm doing here, it's just a random thing. If I wrote square brackets N2, I'm talking about the concentration of nitrogen gas in whatever it is that I'm talking about. Now, because we're not talking about nitrogen gas, I'm going to make that go away very quickly. All right, I'm going to quickly there were a couple more questions. Can I ask, please don't ask any more. I've just got to get back to them. So let's quickly see. Okay, so NO2 in this case should start with the lower concentration because it's the product. We don't usually start with the thing that we're making. You could imagine in the case like an industrial process where you're making ammonia gas, you don't start with the thing that you're making in the reaction vessel. You start with your nitrogen and your hydrogen and you combine them to make ammonia. So we usually assume that you start with a high concentration of starting material and a low concentration or no product. Because it's logical, that's what you're going to be making. If I'm about to start baking cakes, I don't start with the cakes. I start with the ingredients and then I finish with the cakes. So you usually don't start with your products. But once you've made your products, in a reversible reaction, they can reverse and go backwards. All right. Cameron, I presume I've already answered your question. Do we assume that the forward reaction always decreases the concentration? No, the forward reaction will only decrease the concentration of starting materials, and it may not have an overall decrease in starting materials if the reverse reaction is faster. So it depends on how much faster your forward and your reverse reactions are as to which one is going faster than the other, as to whether the concentrations of anything go up. That's why I use the word favored. If the forward reaction is favored, then it will decrease the concentration of your starting materials because you'll use it up. Okay, so we mentioned that the square brackets show us the concentration, and the favored one will always have less concentration. Well, the starting materials of the reaction that's favored will always have a lower, or always decrease in concentration. But bear in mind that starting materials are relative. If I'm talking about the reverse reaction, that's when we go NO2 turns into N2O4. Can you see that according to this, the way this is written, the forward reaction is N2O4 going into NO2. The reverse would be written like this. Some of you may then immediately get on my case and say, but ma'am, if you've written it like this, then surely this is the forward reaction again. So which is the forward and which is the reverse is a perspective, and we assume that the order in which we've written them in always goes starting materials on the left to products on the right, and the reverse has starting materials on the right to the products that it forms on the left. Okay, I know that there are quite a lot of concepts. We'll get through all of them just now. Can I quickly check, have I managed to hopefully undo some of the minefields? Okay, I'm assuming that's good. I'm going to carry on. I'll give you a chance to ask questions again just now. So please remember, we're now going to be applying these things here about identifying the disturbances and removing or counteracting the disturbance. Okay, so there are 3 factors which can distort or can cause a disturbance, can disturb an equilibrium. Those 3 things that we can change are firstly the temperature, secondly the pressure, and lastly the concentration. So anytime that you change the temperature or the pressure or the concentration, you're going to be applying a disturbance to the equilibrium. Now, while we're on this, I need to put the list of things that are not. Please note, adding a catalyst does nothing to the equilibrium. And the reason is that a catalyst will make both the forward and the reaction rates go up by the same amount, okay? So imagining that scenario of me drinking tea in my house and leaving teacups everywhere while somebody has to keep cleaning them. All that's happening with a catalyst is that I'm drinking tea faster and my whole family's running around washing dishes faster. But we're still in the situation where we don't disturb the equilibrium. Both rates go up evenly, okay? So we're still in equilibrium, we're just in equilibrium at a higher rate. But a disturbance to equilibrium will favor one reaction over the other. If you remember our definition at the beginning, was chemical equilibrium is where the rate of the forward equals the rate of the reverse. If one is faster than the other, they're no longer in equilibrium. We can no longer say we've got an equilibrium because they're not equal, all right? So a catalyst will have no effect on the equilibrium. Next thing, when we talk about concentration, we're specifically referring to the concentration of aqueous solutions. That's the AQ. So the next thing is, what about if we add a solid? And when I talk about a solid, I don't mean that a solid that will then dissolve and become aqueous. I mean a solid that's insoluble, okay? So adding a solid that is specifically insoluble once it's been added into the liquid, that will also have no effect on the equilibrium. A lot of people get very uncomfortable with this because you've got a reaction where you're putting in more calcium, well, let's go on it, calcium carbonate, which is chalk, and everybody's like, but the calcium carbonate's got to do something. If it is a solid powder that we're adding and it doesn't dissolve in the solution and therefore change the concentration, it has no effect on the equilibrium. A lot of people really don't like this one because it's very tempting to see it as, oh, we're increasing the concentration of the solid. Hate to tell you, concentration is number of moles per unit volume, and it assumes that everything has to dissolve. Yes, Christine?
Hi, ma'am. Does concentration also apply to gases?
Yes, but it usually would rather fall under pressure. Okay.
Okay,
So
thank you.
when we talk about gases having different concentrations, it's because we've compressed it and we've pushed it closer together. So usually, I guess our concentration can refer to gases as well. Okay, so we can do Kc calculations with gases. You guys don't have to do the partial pressure things that they do at university level to do Kc calculations. So it could also refer to gases. But the point here that I'm making is if you add in a solid, it has no effect whatsoever. Okay. Oh gosh. Dina, how do we know if the substance is soluble or insoluble? There are a bunch of solubility rules that you can find on the internet, but usually the way that you would know is in a chemical equilibrium, they would say sulfur S afterwards to tell you it's solid. So most of the time you're going to just check on your formula and you'll see, wow, cool, we're having sulfur solid added to oxygen gas. This is not an equilibrium. And then we're going to, let's pretend this makes an equilibrium, but I don't think it is. Here you'd go and say, oh, wow, look, that one's a gas and that one's a gas, but this one's a solid. That's how you know it's an insoluble solid. If it instead said aqueous here, you'd know it could dissolve, and then we can, by adding more, change the concentration. All right. So these are the three factors that can change an equilibrium. We're not going to look individually as to how changing them will factor in and how we can use Le Chatelier's principle to answer a question. All right, let's keep going. So I'm going to pick on the same example I always do, and I think most teachers do because it's easy. If I have nitrogen gas and I react it with hydrogen gas, I'm going to produce ammonia. Now, the fact that we have got all three of them with G's, those G's tell us our state symbols, which tell us that we're dealing with gases, which is very important because gases mean that the pressure will be important. So when I mentioned the temperature, pressure, concentration, pressure only affects a reaction if it's got gas in it. If it's solids and aqueous solutions or even pure liquids, nothing happens. Okay. The next thing that we're going to do is, because we're specifically, so this reaction is the one I'm going to look at for all of the three factors and how they affect. The first factor that I'm going to look at is I'm going to look at what happens if we have an increase in temperature. Okay. Now, before we go any further, I need to determine whether this reaction is exothermic or endothermic. I'm just quickly going to move it across because I'm going to run out of space otherwise. And I'm going to tell you right now that this reaction is exothermic. I know that it is exothermic because if you do this reaction, it gives off heat. You cannot, by looking at a reaction, see if it's endothermic or exothermic. There's nothing about the chemicals. If you want to get really technical, you can. You can go and download a table of bond energies and work out the bond energies of your starting materials and how many bonds you have to break and how many you have to make. That's kind of grade 11 work, okay? So what we instead do is we assume that you'll know whether it's endothermic or exothermic by looking at your delta H value. If delta H is less than 0, we know that it gives off heat, which means that this reaction is exothermic. Now, that means that this gives off heat, which means some people even write that energy is a product, okay? I hate doing that. So what I instead do, but I'm going to leave it there for just a second, if the forward reaction gives off energy, then the forward reaction is exothermic. If we now leave the energy for 2 seconds there and we read what happens with the reverse reaction takes ammonia, puts in or grabs energy, and forms the product. That means that our reverse reaction over here is endothermic. So we have a rule that if the forward reaction is exothermic, then the reverse reaction is endothermic. Now, you need to identify, based on what they give you here, whether it's endothermic or exothermic. They may give you other hints. So for instead of writing that delta H is less than 0, they may have said delta H is equal to, I think it's negative 198, whatever it is. They may give you an actual number. They may also tell you that this reaction happens and it feels hot. Okay? Anything like that could be enough of a hint that it's an exothermic reaction. Sometimes the question goes backwards, and this is very common for matric, where they'll instead tell you that an increase in temperature favors whatever makes something happen. Is the whole reaction endothermic or exothermic? So instead of endothermic and exothermic being your starting point, it actually becomes what you're trying to work out. Okay, we're going to take a step back so that I can just go back and answer the question. So the question here would be, what happens to this reaction if there's an increase in temperature? So my first step was to identify the disturbance. So I would say here, according to Le Chatelier's principle, and I'm abbreviating it, you never do that, the disturbance is an increase in temperature. Okay, also not recommended in an exam, up arrow, down arrow, not increase and decrease. This is just my shorthand. So I'm not going to run you through the steps. According to Le Chatelier's principle, the disturbance is an increase in temperature. Therefore, the second step was, what does the system want to do? The system will act to decrease the temperature. So if it wants to decrease the temperature, it is going to effectively, and anything I write in brackets is never going to give you marks, it is therefore going to favor the reaction which absorbs heat. Heat is thermal energy. So it's going to favor the reaction which absorbs the heat, because when it absorbs the heat, it lowers the temperature. What do we call the reaction that absorbs heat? Our exothermic gives off heat, our endothermic absorbs heat. So I'd say, therefore, the endothermic reaction is favored. Okay, so according to Le Chatelier's principle, the disturbance was an increase in temperature. Therefore, the system will act to decrease the temperature or to favor the reaction which decreases the temperature. You may choose either. Therefore, the endothermic reaction is favored. Favored is a very important word here. Our endothermic reaction, you remember when I drew this in, exothermic referred to whatever was for the forward reaction. Endothermic referred to whatever was for the reverse reaction. Technically, these have both got little arrowheads on both sides. So I would then say, therefore, the reverse reaction is favored. Now, what the question may have been here is it may have been, okay, the reverse reaction being favored is that we are going to have more ammonia break down into hydrogen and nitrogen than nitrogen and hydrogen making ammonia. So we're going to be breaking the ammonia down at a faster rate than we're making it if we increase the temperature. All right. Okay, so just quickly, the mark allocation here is usually 3 marks. Okay, would you have to identify the disturbance in each scenario, these hypothetical? I'm going to run you through all of the hypotheticals that you can have when we begin. And then in an exam question, you'll look at the specific question. You'll go, oh, this is the thing that they've changed. So I'm running you through the overview of everything that you can do. And then we'll look at specific exam questions and see what we're doing in each specific case. All right. So this is the overview. So here, usually you'd have to go and say, I think it's that the disturbance is an increase in temperature and therefore it wants to decrease the temperature. I'd say that both of those would typically get you 1 mark. Endothermic reaction favored, reverse reaction favored. Usually if we're giving 3, that's generous. Okay, but the question may also have been a number of things. Once again, I didn't give you a question. I'm doing a hypothetical if, okay? So if this is the case and the reverse reaction is favored, then we could be in a situation where there is a decrease in the concentration of ammonia, because if the reverse reaction is being favored, ammonia is being broken down into nitrogen and hydrogen. The next thing is if ammonia is being broken down into nitrogen and hydrogen, then there'll be more nitrogen because we're reproducing it, and more hydrogen because we're reproducing it. Okay, we can also talk about the fact that the equilibrium shifts. Now, if the reverse reaction is shifted and we're favoring the reverse reaction, that arrow is pointing to the left. So we can also sometimes say that the equilibrium shifts or lies to the left. If we're doing the opposite, we could say that the equilibrium shifts or lies to the right. Please, this isn't saying that the forward reaction and reverse reaction aren't both happening. It's just saying that if we increase the temperature, because the system wants to decrease the temperature, it'll favor the reverse reaction. Okay, so just quickly, Emmy, the explanation of the word favored isn't that only one reaction happens and both don't. It's that one reaction is favored over the other. I'm going to get back to that in a second, so just give me a pause on that. And is this whole chapter of equilibrium in terms of concentration? Pretty much. It's a lot of it isn't in terms of concentration, but when you do all of your Casey calculations, concentration comes back in again and again and again. All right. So I just quickly want to talk about the idea of favored here because it's a good time to. All right. I hope I'm not going too fast for anybody or too slow for anybody. I hope I'm doing the Goldilocks just right. Now, the reason that we talk about the word favored, and this, what I'm writing in red is please not part of anything that I've written before, is that if we increase the temperature, all of the particles, whether they're starting materials or products, will have more energy, which means that we'll have a faster rate of both the forward and the reverse reaction. both the endothermic and the exothermic reaction rates will both go up, okay? Because if you've learned your rates of reaction, one of the factors that affects the rates of reaction is your temperature. And we've always just learned that if the temperature increases, so does the rate of reaction. So the same thing still applies here. If we increase the temperature, so if there's an increase in temperature, the rule here is that both the endo and the exothermic reaction, you can't ever write endo, but you know that I mean endothermic and exothermic reaction rates will increase. Up arrow means increase, but what's going to happen is that in this case, the endothermic increases by more. All right, so I can do my little mental picture. If we increase the temperature, both rates go up. The exothermic goes up from here to here. The endothermic goes up more. So the endothermic reaction rate will be faster than the exothermic reaction rate, which is why we specifically use the word favored. Okay, will you be told in some way whether the reaction is endothermic or exothermic? Yes, you will, or you'll need to figure it out from other information that's given. But it's never going to be something where you're expected to have memorized off by heart whether a reaction is endothermic or exothermic. All right. Ladies and gentlemen, I'm hoping that you've got this idea a little bit. Okay, so I'm just going to quickly recap again one more time. That the disturbance, if the disturbance is an increase in temperature, the system will want to decrease the temperature. To decrease the temperature, you need a reaction which absorbs heat so that the temperature goes down. Okay, if the temperature goes down, okay, then we'll have removed the disturbance. The reaction which makes the temperature go down is the endothermic reaction, which is why the reverse reaction is favored. As a knock-on effect, when the reverse reaction is favored, the concentration of nitrogen becomes less, the concentration of ammonia and hydrogen become more, okay? The key word was favored, that the endothermic reaction is favored, as in favored over the exothermic. The very important bit here that I've got as an NB is that both reaction rates go up. The reason I mention this is that they may at some point ask you, what happens to the exothermic reaction rate? And everybody has this idea that if endo goes up, exo must go down. And then you go, oh, it decreases. That's nonsense. If the temperature increases, both endo and exo, both the forward and the reverse rate go up. But the endothermic reaction, because it's absorbing the heat to remove the disturbance, will go up by more, which means that in this particular case, the reverse reaction is favored. Okay. Did I manage to answer? There were questions and hands up. Are they still up? Yes, Tasneem?
Yes, ma'am.
What's your
So, ma'am,
question?
would they ever give us a rate of reaction graph with this
Yes,
for endo and exo?
yes. Anytime that they want to, but I haven't yet got that far. Okay, they're going to be doing a lot with this. This is not an easy section. Okay, but I've got to teach it to you from the very beginnings, and then we kind of move our way through it. All right, next question. Yes, Tasneem? Okay, I think does that make sense? Okay, cool. All right, now I want to quickly show you what happens on the other hand, and you're just going to have to excuse my laziness, but this is a lot easier and it takes a lot less time. What about if the disturbance was not an increase in temperature? So I'm going to cheat in here. And I'm only going to take out certain bits. And you're going to see that the whole thing still remains and makes sense. Okay. There are quite a large number. I think that usually your equilibrium question is about 17 marks. Okay. But it's not hard. We're going through it slowly. Breathe in, breathe out. We're building this with building blocks. What about if instead the disturbance was a decrease in temperature? Please note, the reaction is still exothermic. Just because we decrease the temperature doesn't change whether the reaction naturally is endothermic or exothermic. So, according to Le Chatelier's principle, the disturbance is a decrease in temperature. Down arrow means decrease. Therefore, the system will act to counteract the decrease in temperature, so it'll want to increase the temperature. This is going to bite me, okay? So it wants to instead increase the temperature, okay? Therefore, it will favor the reaction which releases heat or gives off heat. If you want the temperature to go up, you turn on a heater, something to make the temperature go up. The reaction which releases heat is the exothermic reaction, which is now favored. And the exothermic in this case was the forward reaction, because delta H told us the reaction was exothermic. Please note, whatever information is given here is always given for the forward reaction. Always, okay? So we can therefore say that if this is delta H is negative, that's for the forward reaction. So over here, the forward reaction is favored. If the forward reaction is favored, our concentration of ammonia will increase. We're making more of it. The concentration of nitrogen will decrease because we're using it up. As we use these two up, we will make more of this. It's not that the reverse reaction is happening, it's just not happening as fast. And the concentration of hydrogen also goes down. Okay, so over here, if we have a decrease in temperature, both the endothermic and exothermic rates will decrease, both go down, but what happens is that the exothermic decreases by less, and that is why it's actually favored. So the the exothermic reaction, okay, will decrease, but here the exothermic reaction will decrease by less. All right, okay. I hope that this makes sense. I know if you haven't yet done this, it is a very challenging conceptual thing, but it's one of those where as you practice, you build up the ideas as to whether you're looking for, well, first of all, whether it's endothermic or exothermic, and then what disturbances will do. Okay. All right. How will you tell if or which reaction is forward? They will give you a balanced equation, and you assume that as it's written down, reading it from left to right is the forward reaction. Reading it from right to left is the reverse reaction. Okay. All right. So that, oh my goodness. Okay. Yes. Quickly with the questions. Who's got a question? Yes, Tristan?
That the equilibrium shifts to the right now?
Sorry,
Or does
just
it still...
Oh, yes, yes. Sorry. Thank you. I didn't change that bit. Since
Okay.
let's do all the bits together. Sorry, this is what happens when you fill in blanks. Because we're favoring the forward reaction, the equilibrium in this case would shift towards the product side. So we'd say that the equilibrium shifts to the right. Please note that all of these here are just answers or options to answer what the question may be looking for. And individually, the question can change almost every single time. So I can't even tell you ahead of time what it's going to be. But this is to give you an overview as to how the factors affect things. And then when you go into the exam questions or past papers, you can specifically highlight what kind you should be dealing with. Yes, Tristan, next question. Where's Tristan?
That's it, ma'am. Thank you. That's it.
Okay, brilliant. And Tasneem?
Ma'am,
Yes.
so for equilibrium shifting, it's the side with the less number of moles.
No, not at all. With the equilibrium shifting, if the equilibrium shifts to the right, it's because we're literally favoring the forward reaction. If the equilibrium shifts to the left, we're favoring the reverse reaction. That's what it is that we're looking at. Okay. All right. I'm going to clear this. I think I need to pick up the pace just a little bit. Ladies and gentlemen, at this time, we're a little bit more than halfway in. I'm going to ask everyone just quickly. I know I normally do this, but today's been a little bit crazy. I'm going to ask everyone to quickly stand up and shake their bodies out, because otherwise you're going to fall asleep on me. I know we're doing quite a lot. Just quickly stand up and stretch, and then we're going to continue by looking at the effects of other factors. Okay, I don't think we're going to get quite as far today as I planned to, but I think I also don't want to leave anyone behind on what is a rather challenging section. Okay, so I don't want to go too fast. Yes, Christine, do you have a question? Okay, I'm not quite
No,
certain.
ma'am, sorry. I
Okay,
don't
don't
know
worry.
what happened.
I think you pushed your hand up, but don't stress, that's not an issue. Okay, so going back, I'm going to quickly rewrite the same equation. So it's N2 plus 3H2 in equilibrium to give us 2NH3. Now, I'm deliberately going to put all of the gas symbols back in here. You'll notice that I only care about whether it's endothermic or exothermic when I'm talking about temperature. As soon as I'm talking about pressure or concentration, instead of referring to the endo or exothermic reaction, I'm only allowed to refer to the forward or the reverse reaction. Please, in a question where they change the pressure, don't use any other incorrect terminology. All right, so we're now going to look at what factors, well, what effect an increase in pressure might have on the system. Yes, okay, Zenat, that is correct. All right, so if we increase the pressure, the rule that we've got here is that whenever we look at pressure, we're going to specifically focus on the moles of gas. So what I tried to do at this time is I go and look at here and see that both of those have got gases and this has gas. On the starting material side, I have got 1 plus 3. I have got 4 moles of gas. On the product side, I have only got 2 moles of gas. So what we can say here is the starting material side has more moles of gas. And please don't ever just say more moles, it's got to be of gas. And the products have fewer moles of gas. Now, before we go any further than this, I want to discuss with all of you, do a quick recap about what pressure is. So pressure comes about because of the fact that it is the ratio of our force per unit area. When gases exert pressure, it's because particles of the gas collide with the walls of the container. My hand is the walls of the container, okay? This hand's the walls of the container, it's flat. This one's the particles, and when the particles collide with the walls of the container, they exert a force, okay? You should know that the pressure in a gas comes from how hard the particles collide, how often they collide, how much energy they collide with. But also, and this is what we're going to be focusing on, it's how many particles of gas there are. If there are fewer particles of gas colliding, then there will be a smaller force and a smaller pressure. If there are more particles of gas colliding, imagine this isn't just my one fist, but it's multiple little fists, we will have a larger pressure, okay? So when it comes to this idea, we need to know that more moles of gas exert a larger force and a larger pressure. Okay, sorry, I'm just going to ask for a little bit, if everybody doesn't mind, if I at least get to the end of each section before you ask questions. Because at the moment, I feel like all I'm doing is answering questions. And the problem is it actually slows down the process that I'm going through things. So if you don't mind, I'm going to get to the end of pressure. And then if I haven't answered your question, I'll go back. All right. So more moles of gas exert a larger force and a larger pressure. And if we pick the side with fewer moles of gas, we will have a smaller force on the walls of the container and therefore a smaller pressure or a reduced pressure or something like that. That's just to get the idea as to why we care about this. So when it comes to pressure, the only way that we can have an equilibrium that shifts is if we're favoring the side with the correct number of moles, fewer or more. So our rule here is that according to Le Chatelier's principle, the disturbance is a decrease in pressure. Oh, sorry, increase. I said increase. The disturbance is an increase in pressure. Therefore, the system will act to decrease the pressure. If you want to decrease the pressure, we want a smaller pressure, so we're going to choose the side with fewer moles of gas. The side with fewer moles of gas is our products. In order to turn our starting materials, which have 4 moles worth of gas, into our products, which have fewer moles of gas, we must favor the forward reaction. So the system will act to decrease the pressure. Therefore, we say the side with fewer moles of gas, and you've got to say of gas, you can't just say fewer moles of gas is favored. The side with fewer moles in this case, not every case, none of the rules that I've given you so far apply in every one of the cases. They only apply in a case here where we've got fewer moles of gas in the products than in the starting materials. So the side with fewer moles of gas is favored, and therefore we can say that the forward reaction is favored. All right, so that means that we could then say the forward reaction is favored, concentration of ammonia would go up, concentration of nitrogen and hydrogen would go down. Because we're making ammonia, it'll have more. Because we're using nitrogen and hydrogen, it'll have less, okay? We've actually got to be a little bit careful because sometimes, I should rather not, instead of saying the concentrations will change that way, sometimes by increasing the pressure, we've actually done so by decreasing the volume. Because we've decreased the volume, you think about the fact that concentration is number of moles over volume. By decreasing the volume, I may actually have increased the concentration of everything anyway. So just be a little bit careful on answering those. I know I went and said concentration of nitrogen goes up and concentration of ammonia goes up and concentration of nitrogen and hydrogen goes down. But we probably should just say that there are more moles. There's a higher yield of ammonia and a lower yield of nitrogen and hydrogen, rather than speaking specifically here about concentration, because sometimes the way that we created this high pressure was by decreasing the volume. So it's just a little thing to be aware of. We can also say here that since the forward reaction is favored, that the equilibrium shifts to the right. Okay. Yes.
Does ma'am mind explaining again why we are favoring the forward reaction, please?
Okay. So if you look here, do you agree with me? Who was speaking? Was it Hussein?
Yes, ma'am.
Okay. So do you understand? Tell me in this case, what is the disturbance?
An increase in pressure.
Good. And the system always opposes or counteracts that disturbance. So what's it going to do?
It will decrease the pressure.
Good. Now, if it's decreasing the pressure, does it favor the side with more or fewer moles of gas? Pressure in a gas is linked to the number of moles. So if you want to decrease the pressure, you must favor the side with fewer moles of gas. Yes? If we look here, right at the beginning, I started saying that our mole ratio says that if we have everything on the left-hand side, we'd have 4 equivalents or 4 moles of gas. Technically, when we're talking about moles here, we're not talking about proper moles. We're just talking about mole ratios. So here, we would have 4 moles of gas, where if we instead turned these into ammonia, they're only 2 moles of gas. So we literally count anything with the G and the number in front of it, and we add all of those together, and we see what number we get on both sides. Because we need fewer moles of gas, we're going to favor forming the products because we've got 2 moles of gas versus 4 moles of gas. Does that make sense?
Yes, ma'am.
So if you want to favor the side, I've said side with fewer moles of gas is favored. You could also have said we favor the side with fewer moles of gas. If you look here, 2 is smaller than 4. To make the products, you push the forward reaction, or the forward reaction happens, which is why we say that the forward reaction is favored and that the equilibrium shifts towards the right, because in this case, the forward reaction being favored means our equilibrium is towards the right. Okay, quick question. If the number of moles are the same on each side of the equation, then there will be no disturbance to the equilibrium. So this pressure only has an effect if you've got one side with more moles of gas than the other. Otherwise, it does nothing. If everything is solid or aqueous, it does nothing. There is no effect on the equilibrium. So then pressure has no effect. Ma'am, would they ever ask us to calculate the number of moles using PV as nRT? I haven't ever seen it, okay? There is allowance for anything that's been taught in grade 10 or 11 to come up in a matric question, but as a side question, not as the main focus. So here, what you're doing is effectively you're using PV as nRT. You're just saying that P is proportional to N. So if the number of particles goes up, so does the pressure, but that's the full extent that you use it at. All right, Alex, if we favor the side with fewer moles, then it would produce more moles, increasing the pressure. So how does this decrease? Okay, so just quickly, if you favor the side with fewer moles, no, favoring the side with fewer moles wouldn't produce more moles. It would favor, so if we favor this side, we're now producing ammonia, where there are half as many moles of gas, which means that effectively have fewer collisions with the walls of the container and the pressure would drop. Okay, last question before I continue. Wow, this concept is basically opposites. Gabriella, I'm not quite certain if what you mean. If you mean by its opposites is that what removes the disturbance is the opposite of what created it, then yes. Okay, that is what we're trying to do here, is the reaction which undoes the disturbance, according to Le Chatelier, is the reaction that's always going to be favored. Le Chatelier's principle says that a system in equilibrium, when it's disturbed, will favor the reaction which counteracts the disturbance. Okay, so if we've got a situation where the pressure is increased, the way to remove that is to decrease the pressure. The way we decrease the pressure is we favor the side with fewer moles of gas. Because we favor the side with fewer moles of gas, we'd favor either the forward or the reverse, depending on what particular ratio you got in a particular balanced chemical equation. All right, I'm going to quickly do the changeover for what would happen here if this had instead been a decrease in pressure. So I'm going to try and do this without leaving any of the silly ones off. Okay, so I'm doing this in a different color so I can check it. The disturbance is a decrease in pressure. The way that we decrease the pressure is we increase the volume. Bigger container means that we'll have a lower pressure, fewer collisions with the particles because they take longer to go from one side of the container to the other. So according to Le Chatelier's principle, the disturbance is a decrease in pressure. Therefore, the system will act to increase the pressure. If we want to increase the pressure, we need a larger pressure, so we need the side with more moles of gas. Therefore, the side with more moles of gas is favored. In this case, the more moles of gas is your starting materials. So we can say here that the reverse reaction is favored because that is going to produce 4 moles of gas instead of 2 moles of gas. Okay, so because the reverse reaction is favored, that arrow points towards the left. Therefore, the equilibrium shifts towards the left. Okay. Yes, in this case, we're now going to favor the reverse reaction because that's what happens. All right. Perfect. So I think I've managed to get through most of the questions. The questions are going to kill me. So, no. Okay, there's a question here saying, ma'am, wouldn't an increase in volume increase the pressure, not decrease it? According to Boyle's law, pressure and volume are inversely proportional. If you remember, the pressure comes from the collisions of particles of gas with the walls of the container. If I make it a bigger container with a bigger volume, with the same number of particles, those particles will take longer to hit each wall because they've got to travel further. So we'll have fewer collisions and lower pressure. So we always have a situation where the smaller the volume is, the bigger the pressure is. If you were to think of a balloon and you squash it, you're decreasing the volume. And by decreasing the volume, you're increasing the pressure. On the other hand, if you have something and you give it a bigger volume, the pressure will go down considerably. So pressure and volume always go in opposite directions. Okay, so that was the second factor that we've been looking at here that's going to affect the equilibrium or disturb the equilibrium. So far, we've looked at the effect of temperature and the effect of pressure. Please remember, in pressure, we're not going to be talking about the endothermic and the exothermic reaction. Those are specifically limited to anything that involves temperature. Okay, all right, I'm going to quickly clear everything here. Yes, quickly, Iman. while I'm quickly setting everything up again? Speak up, and then Christine.
Ma'am, are we expected?
Yes,
Sorry.
Simon?
Ma'am, are we expected to know Boyle's law and that for matric exams, like our last year's definitions and that?
Do you know what? The problem with all of these is I can't tell you with certainty you don't need to know them, but I can tell you that they're never going to be the focus of a question. So according to the CAPS curriculum, if you go and read it very carefully, it says right at the beginning that anything that we've taught you in grade 10 or 11 can be examined. But usually if they bring in those things, it's for 2 marks here and 2 marks there, and it contributes a very small quantity of your total paper. So it's usually a good idea to understand all of the work that you should do, because there's applications of what I was just saying with Boyle's law, where maybe the question doesn't tell you that the pressure goes up. Maybe it tells you that we've got a container and we compress it, or we make the volume smaller, and you've got to figure out that making the volume smaller means the pressure gets bigger. So there are little things like that where it's never going to be the focus of a question. But sometimes if you don't understand that, you miss what the question is. So there are quite a lot of little things like that which can come up. But I don't want you to get your knickers in a twist about them if you don't understand them. Obviously, if you have an opportunity to go back and to revise them, I would suggest it, but not at the expense of your current matric curriculum. Get through your current matric curriculum first. If you've got time, go back and look at the other little things that you may have missed. But it's just little things. What I find is as soon as we hit them, I raise them up in different questions that maybe if you don't know them, now you've just had a little refresher on Boyle's law. Pressure and volume go in opposite directions. Okay, so I wouldn't get any sleepless nights over it. Okay, the last thing that we're going to do is look at concentration. And concentration for me is by far the easiest, but it's also the thing that's most open to weird things happening. So when it comes to pressure and temperature, we had 2 options. We increase or we decrease. When it comes to concentration, we can increase or decrease nitrogen, increase or decrease hydrogen, and increase or decrease ammonia. We could do any one of those. In this question, there's 6 options of what we could do. We're not ever going to do all of them. I haven't ever seen a question where they've changed more than one variable at a time, but any of those could happen. So I'm going to just pick on one of them. I'm going to say that the disturbance is an increase in the concentration of nitrogen. Can you see that I'm using square brackets to indicate that there's concentration? So square brackets, remember, tells us that we're dealing with concentration. So I would say here, according to Le Chatelier's principle, the disturbance, and please, you only write out this whole thing that I'm writing out now if they say use Le Chatelier's principle. Otherwise, you think it in your head and you write straight to the answer. So according to Le Chatelier's principle, the disturbance is an increase in the concentration of nitrogen. Therefore, what does the system want to do? The system will act to, can anybody tell me, what will it do? Come on. The disturbance is that we increase nitrogen. What's it going to do? Okay. It's going to decrease the concentration. Guys, you're missing the point. Decrease. You got to finish the sentence. Disturbance was increased concentration nitrogen. So the system is going to decrease concentration nitrogen. You're not going to get away with just decrease. Okay. So, yes, we normally talk about, okay, these are gases, but we're allowed to talk about concentration of gases as well. Okay, so the system will act to decrease the concentration of nitrogen. Technically, concentration is moles per decimeter cubed, and we are allowed, although it's not probably the best way to do it, but we are allowed to do it here in the case of gases. So just, I understand why you're saying Shirley, ma'am, and I agree with you. We're just going to go with it. Okay, so the system will act to decrease the concentration of nitrogen. How can we make there be less nitrogen? If we favor the forward reaction, we're going to make nitrogen, and the nitrogen will go up. So that isn't going to be the right approach. The only way to make there be less nitrogen is for us to turn our ammonia. Sorry, I'm saying nitrogen, talking rubbish. Oh, wrong way. My brain is dying. Apologies, that was me hitting 8:20. I'm on the wrong side. Sorry, everybody. I'm pulling myself back together. Okay, let's keep going. According to Le Chatelier's, I'm looking at ammonia, brain dead. So according to Le Chatelier's principle, the disturbance is an increase in the concentration of nitrogen. The easiest way to get rid of that nitrogen is to use it up. If we turn that nitrogen into ammonia, we will decrease the concentration. So we can say here, therefore, the forward reaction is favored. Favored, since it will use up the nitrogen. Okay, so since it uses up the nitrogen, it'll remove the disturbance and use it up. So therefore, our answer is quite simply the forward reaction is favored. If we wish to, we can say that the equilibrium shifts to the right. Now, we could do this for anything. We could look at the situation where our disturbance was maybe instead that we have a decrease in the concentration of ammonia. So if we have too little ammonia, the disturbance will be a decrease in the concentration of ammonia, and the system will therefore act to remove the disturbance, which means we must increase the concentration of ammonia. If we need to make more ammonia, we must favor the forward reaction to do it. So the forward reaction is still favored. In this case, not because it'll use up nitrogen, but because it will produce ammonia. And the equilibrium will still shift towards the right. So what we do in an industrial reaction to make sure that we push these reactions that we want to have happening in the directions we want to have them happening is that we're continuously going to choose to put in more starting materials. And instead of waiting for our products to break down, we're going to continuously remove the products. In industry, we're not aiming to have things that we make that break down at the same rate as we make them. If you're trying to use the Haber process to mass produce ammonia, the fact that the ammonia that you've just gone and made is breaking down is completely against the principles of industrial production. You would want to make ammonia, remove the ammonia, sell the ammonia. You're not going to wait for it to go, oh, it's cool. It can just break down to its starting materials. It's no issue. So we always pick conditions that make these reactions occur. All right. No, in this case here, because the forward reaction was favored, as soon as the forward reaction is there, it's the direction that it's pointing in. So the equilibrium will shift towards the right. Sorry, that was just me quickly answering a question. All right. Ladies and gentlemen, these are the factors which will affect a disturbance. Okay. Now, there's one last thing that falls under concentration that I just quickly want to discuss because it's one of those things that pops up. And it's not a large amount of marks, but it's a good couple of marks that you don't want to throw away when you don't have to. And this effect is known as the common ion effect. Okay. We're nearly at the end. I'm going to encourage you to stay right till the end because I'm going to keep teaching right till the end. But before we go any further, I want to just quickly ask, who has ever heard of the common ion effect? Hands up if you've heard of the common ion effect. Okay, 5, 6, 7, 8, 9, 10, 11. Okay, well done. You guys have got good teachers there. Fantastic. Some of you may not yet have done this. But the common ion effect is one of those things that often gets overlooked. And I always use the same example to teach this, but I'm also going to show you other examples of weird things that come up that can be done. So my favorite example for this is if we take sodium chloride, which is a solid, and we put it in water, it can turn into Na+, which is aqueous because now it's dissolved, and into Cl-, which is also aqueous because it's dissolved. And what is observed is that when HCl, hydrochloric acid, is added to the above equilibrium, I'm pretty sure this is even the example most teachers used. So when it's added to the above equilibrium, what it does is we suddenly observe that a white precipitate forms. PPT is the abbreviation for precipitate. That's something that's solid and doesn't dissolve. Okay. And the question often asks you to explain what happens. Now, what's happened here is by adding HCl, I've added H plus and Cl minus. Even though HCl is not there or there or there, as soon as we add the Cl minus is common to this. So what's happened is by adding HCl, we have indirectly had the concentration of the chloride ion increase. It is common to both the HCl and one of the reagents. And because of that, what's going to happen is, according to Le Chatelier's principle, I'm doing the head thinking here. This is one of those where the question maybe didn't tell me to. But the disturbance is an increase in concentration. Therefore, the system will act to decrease the concentration by favoring the reverse reaction. When the reverse reaction happens, we make the sodium chloride solid, and that is the white precipitate that forms. So sometimes we can impact concentration in an equilibrium by adding something that isn't one of the reactants, but interferes with the concentration of one of the reactants. So I'm now just going to mention to you a couple of sneaky things that can change the concentration of something else without you realizing. Okay? So the first one that's very important is if I have H plus reacting with something else in equilibrium to produce something else, and I add in OH minus, any base, what can happen is that this base and this acid react together. And what can happen is that by adding a base, kind of through the common ion effect, there isn't actually another name for it because there isn't anything in common. It's kind of like an anti-common ion. Okay? By adding a base, we can decrease the concentration of H plus. And if the H plus is a starting material, that would favor the reverse reaction. Okay? If I added in an acid, so this is an alternative here, if I maybe, by adding in an acid, we could also have the same thing where we increase the concentration of H plus. Usually the adding of the acid is easy because you can see that it's a common ion, but sometimes the adding in the base and the realizing that you remove the H plus in the form of water is a bit of a sneaky one that goes out. Something else that we can sometimes do, and please, these are very much the higher grade examples, is you should know that if we have Cl minus or Br minus or I minus in our reaction anywhere, and they react with something and they do everything else, and I add in here the silver plus ion, usually it would have had to come in with silver nitrate, because silver nitrate is the only aqueous or dissolving form of silver. These will very quickly form a precipitate. Silver chloride, silver bromide, and silver iodide are all precipitates. And because they react so quickly together, in fact, you may have learned about them in grade 10 because those were the tests that you did for your chloride, bromide, and iodide. Some schools skip them a bit, or it may just have been a really long time ago. But as soon as you're adding silver ions to any of those, it can also, even though silver has nothing to do with it, it can remove it from solution. Now, these three examples that I've given you right at the end, okay, the unusual ones, are often the questions that they put in to differentiate your kind of really high 80s and 90s from everybody else. Because somebody commented a little bit earlier about what do you need to know from grade 10? Well, this is kind of the thing that may come back to bite you. And it's only your really, really strong chemistry students that have kept full tabs of, oh, but of course silver forms a precipitate with a halide. That's what you know. But not everybody knows that or remembers it anymore. So these are just the little things that you need to hopefully keep in your head so that if you see them, they're not, there's a very slim chance that they do come up. But if they do come up, they're going to be your challenging questions on the paper. All right. I am now going to stop sharing because it's been a really long session. I was hoping that we'd get into the chemical equilibrium calculations today because I think that that is the one that a lot of you really need help with. Can I quickly just ask before I go any further, because I always really like feedback as to whether what I've been doing is what people need help with. Who found that what we covered today assisted them with what they needed to know now? Okay. All right. Cool. All right. No, my goal is reached. Do you know what? There are a lot of you, and if I reach even half of you, even if it's slowly, it's something better than where we were. So what I'm going to do when I see you all again on where are we? Wednesday, I'm going to see hopefully some of you for stoichiometry. But once again, if you can't make it, I will be posting the video up. And then on Thursday, I'll go back to the precipitation in just a second. All right. So just quickly to give you an idea, on Thursday, I'm going to be jumping into KC calculations. Please, can I suggest, if you've already done them, that you go back and revise just a little bit. This is one of those sections where we do see a huge difference between the people who get 2 marks out of 17. There are lots of them. This is one of the sections where people leave it blank in an exam, okay? Makes it really difficult when you're marking it because you've got to go the whole way through the paper and make sure it isn't there. There are a lot of people who leave this section out, but it's one of those where you can differentiate yourself, which is why it's so important to do so. All right. So ladies and gentlemen, just because we're already at 8:30, I'm not going to go over time today, but we'll be jumping straight into KC calculations. Please remember to go on to Siavula and practice this section, because I know with this section, we're going to need to do a serious masterclass for the people that are right at the top, those people that are aiming to get 18 out of 18 or top marks for this section. All right, now, while you're going, I'm just going to go back and continue for the people that were asking. I've had a couple of people saying, please explain the precipitation part again, and I will happily go forward to it again. All right, so I'm just quickly gonna share my screen. I'm gonna go back to my whiteboard. Okay, now these really aren't examples, so I'm gonna stop and I'm gonna go into them one more time. So if I were to say, for example, that I have, what was the example before? NaCl solid, and it is reacting, I can do it this way as well, with Na plus aqueous and Cl minus aqueous. So this is a typical dissolution reaction. You take salt, you stick it in water, you stir it. Most of it dissolves, but if you add enough, some of it won't dissolve and it'll remain as a solid. Now, if I were to add AgNO3, my common ion that I'm adding, there's an Ag plus that I'm putting in, and there's an NO3 minus that I'm putting in. And what's going to happen is that the silver in silver nitrate is the only soluble silver salt. Anything else that's got silver in it is going to form a solid, always, okay? So this silver will react with this chloride, and it will form AgCl, which is a solid. In fact, it's a white solid. Okay, now the reason I couldn't start this one off with the white solid forms is that we actually are going to have another white solid forming. But if we're not caring about the white solid that forms here, if we're just caring about is the forward or the reverse reaction being favored, by us having silver and chloride joined together form a solid, the concentration of Cl minus will totally decrease because all of it's bonded to something else and disappeared. Okay, a weird bad analogy is you could imagine these as 2 single people, and as soon as they get married, that person's no longer on the market. They're no longer part of this game because they're married and they're taken out of it completely out. So because of this, adding silver chloride decreases the concentration of chloride ions. So according to Le Chatelier's principle, the disturbance is a decrease in the concentration of chloride. Therefore, the system will act to increase the concentration of chloride. The only way that it can make more chloride is to favor the forward reaction, because then more of the salt that's present dissolves and turns into sodium and chloride ions, and the concentration of Cl minus will go up again, okay, to remove the disturbance. So this is just one of those weird things where adding silver nitrate can affect an equilibrium, even though silver is not one of the reactants. So we can't say that it's a common ion, because it's not common with anything. It's not there. All right, quickly seeing the questions. Whew, I'll go back to the acid and base reaction, but you guys are now asking me to make up stuff again, and it gets tricky. I'll try in a second. Ma'am, why doesn't the NO3 minus react with the Na plus? It might. I mean, we're going to have ions left over, but if we make NaNO3, it's both still aqueous. They're ions that aren't going to form a precipitate. So the Na plus will remain as aqueous, and the NO3 minus will react as aqueous, and the concentrations won't be changed. It's only when we have two ions that bond together to make, effectively in this case, a solid precipitate, that they're no longer going to remain in solution, and their concentration will completely disappear. Okay, not completely. It depends on how much silver we add and how much chloride there was, but it'll reduce drastically. All right, the next question, is this a reversible reaction? Yes. The reason I can see it's a reversible reaction is because of that symbol. So what would happen, you can do this at home right now, is if you take salt and you put it in water, you can put in salt, and eventually you'll find that you reach the point of saturation, which is where you've got so much salt that some of it remains solid. Yeah. And what's going to happen is it isn't just a container with salt grains at the bottom and liquid in. What's going to happen is slowly but surely some of those salt grains are going to be dissolving and turning into Na plus and Cl minus, and some of the ions are going to be combining back together and forming the solid again. So it's kind of a dissolution, and then, yeah, they dissolve and then they precipitate, and then they dissolve and then they precipitate. So there is a bit of an equilibrium that's set up here as well. All right. There was one question about the acids and bases. Now, the problem with these is you guys are getting me to make up questions, and I'm doing them off my head, which isn't a very safe thing to do. All right. How would you know that NO3 would be aqueous? Don't worry. It isn't a silly question. Nitrate, the nitrate ion, NO3 minus, will never form a precipitate. You remember I mentioned somewhere earlier on in the lesson, somebody said, how do you know if it's a solid? And I said, you check the list of solubilities. There is a list, and one of the rules on it is that all nitrates are soluble. You can't make any nitrate that won't be soluble. So all nitrates will always be soluble with absolutely no exceptions. Unfortunately, with these kind of things, they are almost like facts that you build up a knowledge of over time. And you'll notice that when I teach, I often throw them out. And the reason is my background's in chemistry. And I find that not everybody has the same background information. So me saying to you, oh, by the by, nitrogen dioxide's brown, is because it might come up that you need to know that nitrogen dioxide is brown. You may also need to know that all nitrates are completely soluble in any aqueous solution. Okay. In the exam, will they let us know which are solids, liquids, and gases? Usually. The only time they wouldn't is maybe if that is the point of the question and they're testing it. Ma'am, wouldn't the concentration, Na decrease? No, because the Na and the NO3 are both still dissolved in solution. They hang around each other, but they're not really bonded together. When things are a solid or form a precipitate, they're bonded like tide. When we've got sodium nitrate in solution, they kind of know each other, okay? But they're not bonded. As soon as ionic substances dissolve in solution, they dissociate, they separate out as ions, and then they kind of hang around each other because a positive and a negative attract, but they're not together. It's a very casual relationship. Okay, all right. So in this case, now this is very tricky. Is the adding the silver nitrate the disturbance? No. The adding the silver nitrate causes the disturbance, which is a decrease in the concentration of chloride ions. So it's actually the concentration of chloride ions decreasing that is the disturbance. Okay, so it gets, you see, there are a lot of nitty-gritties that come out when you start doing past papers, and they often surprise you because a lot of them are things where you're like, I didn't know that happened. But the more you practice, the more used to the unusual things happening, you get used to it. I guess my advantage here is that I studied chemistry. So I played with these chemicals and I made them do the things, and then I'd see what happened or didn't happen. And kind of the more you get exposed to it, the more you understand it. All right, so I am going to try and expose you to it without you scaring, because I think that's the other problem with this, is sometimes when you get too much information, all that you do is you clam up and you go, my gosh, can't do chemistry. That isn't what I want at all. I want you to go, new little interesting fact for my head. All right. In the HCl addition to the Cl in the products, the white precipitate formed was your sodium chloride. Do they always dissociate and form a precipitate, decrease in concentration of chloride, or do they sometimes increase? Whoa, okay, I'm not quite certain. Amin, are you still here?
Okay, so basically what I'm saying is, for the previous example, we had the chloride in the products, and then we added the HCl.
Just give me a second so I can quickly rewrite it for you. So we had NaCl, aqueous, and then we broke, solid. Yeah, and then we broke it down into Na plus aqueous and into Cl minus aqueous, yeah?
Okay, so here it was said that the Cl will form a precipitate, which will therefore decrease the concentration of Cl in the system.
What happens here is that if we add HCl, we are then adding H plus and we're adding Cl minus. The Cl minus that we're adding, even though it came from HCl, HCl is a strong acid, so the H plus and the Cl minus dissociate, okay? So by adding HCl, the disturbance is that we've actually increased the concentration of the chloride ion. And therefore, according to Le Chatelier's principle, the disturbance is the increase in the concentration of Cl minus. So what the system will try to do, or will act to do, the system will counteract to decrease the concentration of Cl minus. To decrease the concentration of Cl minus, we must use it up. And if we're using it up, the only way we can use it up is by favoring the reverse reaction. So therefore, the reverse reaction is favored. It's a totally different question to the one I did 2 seconds ago. The reverse reaction is favored, and therefore we're making more solid. So we could say that there will be more NaCl solid forming. So you will notice if
so the NaCl is the, sorry, ma'am. So the NaCl is the white precipitate that formed and not the chlorine.
No. This
okay, thank you, ma'am.
Forms. And you normally would not see this NaCl forming unless you'd added lots of salt to the solution. The salt is pretty soluble in water. But if you were to take a container of, I don't know, just a glass, a colorless glass like this, fill it with water and add salt and add salt and add salt and stir, 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 you'd eventually get to a point where there'd be salt sitting at the bottom that doesn't dissolve. And that salt that doesn't dissolve is this salt. Okay, the salt which has dissolved in the water and what you'd call salt water is that salt. Okay. All right, ladies and gentlemen, I'm going to have to go now because I've got to get back to my family. But can I just double check, have I managed to get through most of your questions? This is one of those challenging sections. Yeah, quickly, Dina.
Sorry, I just wanted to ask you, when I said earlier, if the mole ratio on each side of the equation is the same, yes. I wasn't talking about an increase in pressure. If it was an increase in concentration of one of the products.
Oh, no. The only thing that will ever be affected by mole ratios is moles of gas. So if we've got here, this is 1, 1, 1. I mean, it's not going to affect anything differently for either temperature or concentration. So the mole ratio only ever affects the pressure and only if you've got gases. So if you've got 2 gases and you've got an equal number of moles on both sides, increasing or decreasing the pressure will not favor the forward or the reverse reaction, okay? But anything else, I could give you any reaction and it doesn't matter whether you've got the same number of moles on both sides or not, it's not going to have an impact. The only one that does have an impact is if you're dealing specifically with pressure and you've got gases. If you've got an equal number of moles of gas, then pressure changes have no effect, but nothing else will be affected by the specific mole ratio. It has no impact on it. It will affect our KC calculations, but that's about it. All right, ladies and gentlemen, I know we've gone over a little bit, but I think there was quite a lot towards the end and quite a lot of people who got it but didn't. So I'd rather that we went through it and you got it and got it. All right. So
Ma'am, please can you go back one of your pages just to the acid part?
I didn't do the acid part. I'll quickly go back and read
You
it.
wrote something down.
I can't go back easily. So let's just quickly do an example.
It was the H plus.
I
and
just made it up because there was nothing else there. So if I have an example, I'm just trying to think how I do this. If I have H2, now I'm totally making up an example. This is probably not an equilibrium at all. So please just bear with me. No, let's do another one. So if I have H2 and Cl2, I think I can do this with H2 and I2. I think it'll allow me to do it. H2 and I2, I can maybe go and form HI. Let's pretend. Okay, we're very much pretending here. Anybody who's watching this, don't go and criticize me. So if I now am able to pretend that that is made up of an H plus and an I minus, but it isn't really. If I add NaOH, okay, so let's pretend we've got something where we can actually make it acidic. If we add this, what it can do, oh, this isn't an example because we can't even do this. I've got to try and come up with another one. Just give me a second. I'm not allowing myself to make up nonsense. It doesn't work well. So I'm actually going to deal with the proper acid-base reaction. So if I have, let's just go H plus X minus goes to HX. Yay, I've made up something that doesn't exist. Okay, so let's pretend that those two join to form this. If I add sodium hydroxide, it is a base. And what it will do is the base in it, the hydroxide in it, will react with the H plus. So what that'll do is by adding sodium hydroxide, the actual disturbance is a decrease in the concentration of H plus. So according to Le Chatelier's principle, the system will act to increase the concentration of H plus, which means that it will favor the reverse reaction. And when it favors reaction, there we go. And when it favors the reverse reaction, we can also add in here that the equilibrium shifts.
Okay, thank you, ma'am. Yeah, that makes sense.
Does it make more sense? But it's one of those weird things where if instead of adding in a base, I'd instead have added an acid, then adding in an acid would increase the concentration of H plus, and the forward reaction would happen instead. All right. Thank you, ma'am. Yay. All of these are thank you. Would they ever add an amphilite? No. So it's usually weird things that they do in here where they just add stuff. And it's usually the question where it catches you in an exam because you're looking at it going, I didn't learn that reaction. And that's when if you ever think I didn't learn that reaction, you've got to broaden your mind and go, okay, what else do I know that I can apply in this situation to make it a sensible argument? Sometimes, I must tell you, I've got an honors degree in chemistry, and sometimes I look at some of the things and I go, I can make a sensible argument in both directions. So it's not always the easiest thing to do when you're not 100% certain. It's easy if you've got Google. Google can answer most questions. When you're in the middle of the exam and you get something strange like this, at best, just go and look for a common ion, or look, I don't know what the term is when they're common anti-ions, like this. Maybe we'll just call them common anti-ions. Then there's sometimes things that have the common ion effect by removing that ion. Anyway, ladies and gentlemen, I really have to say goodbye now, so I'm going to quickly clear and stop sharing and say goodbye to everybody. Thank you very much for staying right till the end. I know this one's gone a little bit over, but hopefully that makes a lot more sense. And when I see you again on Thursday, we're going to carry on with KC calculations. Hopefully we'll also get to graphs, but graphs is also quite a big challenge on its own. We'll get